We're very happy to welcome Sanjit Seshaya, who's a professor at UC Berkeley. Sanjit is a long-time friend and collaborator. He's visited us many times, and today he is giving a talk on algorithmic improvisation for dependable and secure autonomy. And my guess based mostly on the PLDI paper recently, or maybe broadly many other things as well. Yeah. Okay, welcome, Sanjit.
All right, thank you, Sriram. It's always good to be back. And in fact, today's talk is really a combination of two previous talks I've given here on previous visits. So back about 4 years ago, I spoke about algorithmic improvisation, which is at the time we had just done the theory, some of the initial theory work on it. So it was really more of a theory talk in the sense of CS theory. And then later, when I was here for a longer period of time, 2 years ago, I talked about our work on semi-autonomous systems, autonomous cars interacting with humans. That's the second part. And really, this talk is where both of those come together. And it's, as usual, work that's joined with many excellent students and postdocs and colleagues. And in particular, Daniel Fremont, whose name you see at the beginning, is the PhD student who did much of this work. And so a lot of credit to him about what I'm talking about today. So the context for a lot of our work here is what we call human cyberphysical systems, which is, so cyberphysical systems are computational systems interacting with the physical world. And human cyberphysical systems are CPS, where they also interact with humans. And that's a critical component of the overall functioning of the system. So there are many examples shown here on the slide. So at the bottom right, you can see cars with self-driving features, not fully self-driving, but there's a person in the car whom the system has to interact with. There are people outside the car that it also has to interact with. You also see things like humans working with robots, like in the top left, or robotic surgery and things like that, right? So these things are already becoming real. And many of them, as you can see in this picture, are safety critical. And they also, are systems that operate in fairly complex environments, like cars with self-driving features. So the challenge of ensuring their safe and correct operation is, quite a large one. And we've just, if you have been following the popular press, you know that this challenge has already, caused some unfortunate incidents. Like this is a picture of the investigation of the fatal Uber crash. And while the final report is still not out yet, last year in the initial report, there were hints that software and algorithms, and especially it could be AI, machine learning based perception algorithms, could have been one of the factors. And so if you look at a snippet from the report, it says that, in fact, the car's detection, the perception system, observed this lady who was walking her bicycle across the road in front of the car that was in self-driving mode. And that happened 6 seconds before impact, which is, for a reasonably alert driver, enough time to avoid the collision. But in fact, the vehicle was confused about what it was seeing. And so there seems to be certainly some hints that the perception played a role. And as we all know, AI and deep neural networks are very commonly used in perception these days. So it's conceivable that we don't know the details, but it's probably a deep learning-based system may have been used there. Okay, so that's just an example. So in my group, what we try to do is take formal methods, which is an area this lab knows well, which are really mathematically based techniques that are also algorithmic, that are also automated to model, design, and analyze systems. And about 3-4 years ago, I and my colleagues, we tried to understand what are the special challenges that AI-based systems bring to the problem domain, right, for ensuring correctness and verifying these systems. So that's the paper we wrote down there. And what we're trying to do is prove rigorous guarantees about the safety of the system when that's possible. That's not always possible because these systems are very complex. And also the environments are probably impossible to model in complete generality, right? To capture all possible behaviors in a sound way. And so what we at least want to do in those situations is use formal methods to guide the search for bugs or unsafe scenarios, and to do that in a way that complements work on testing and simulation so that you gain higher assurance, okay? So a lot of what I'll talk about today is really more on the second category. Okay, but this talk really is also about this topic of algorithmic improvisation. So far I've just talked about the challenges in autonomous and semi-autonomous systems. So what this talk is about is that randomness can actually play a crucial role in the use of formal methods for improving safety and security of autonomy. Okay, some of the places where we found randomized algorithms to be useful is first of all in modeling, not just randomized algorithms, but also formalisms that can capture randomness, is in, first of all, modeling autonomous systems and their environments. Then in doing verification, and here we're actually trying to draw inspiration from the use of randomized algorithms in hardware verification and verifying chips. So things like constrained random simulation and probabilistic verification. And then finally, we also are looking at the use of randomized algorithms in synthesis, in synthesizing plans or control strategies for autonomous systems. But the idea here is that the plan or the controller itself is randomized, is a randomized algorithm, okay? And what we found is there are problems where you really want that, okay? All right, so just to summarize some of the contributions that I'll speak about today. So I'll talk a little bit about randomized controller synthesis. This is based on work that was presented at CAV last year. And the idea here is for a robot to produce lots of different trajectories for the robot to explore. So there's a diversity, but it's also each of them obeys safety. Okay. We've also done a lot of work on modeling human behavior. And as one can expect, human behavior is random in different ways, right? So the same person exhibits different behavior on different days at different times. And of course, a population, there's usually some variety over their behaviors, okay? So if you want to model human behavior for these human CPS, then it turns out randomness is useful. And then we've also recently used it for systematically training and testing machine learning models by generating diverse and tunable data sets. Okay, and the nice thing really here is that these three looks like very different applications, but the core theory that's behind all of this is the stuff I talked about 4 years ago, which is this topic of algorithmic improvisation. Okay, so first what I'll do in the next few minutes is give you a little bit of more detail on these applications about where randomness comes up, and then I'll talk about improvisation. Okay, so this first application, the most recent one that appeared at PLDI, so already appeared, not to appear, is about training and testing something that generates data. A generator for generating training and test sets for a neural network that does object detection, in this case, detecting cars, right? So what you'd like to do is generate a diverse data set, okay? And the challenge here is that if you say, okay, the scenario I want to test the neural network on is bumper-to-bumper traffic, then even that, right, there's not one way in which bumper-to-bumper traffic manifests itself. And you've seen 3 photographs down here where the environment around the traffic is different, the lighting conditions are different, the time of day is different, the spacing between cars may be different, the models of cars, the colors, there's lots of details that can be different, but they all share some common characteristic, right? And so if you're generating the data, you want to be able to cover this, and randomness helps you do that. Okay, another reason for randomness is, again, in modeling human behavior. So here's an application where, suggested by one of my colleagues, actually. The idea here is that if you're away from your home on vacation for a while, but you want to make sure that potential burglar doesn't know that this home is unoccupied, then you get these devices which turn lights on and off at certain fixed intervals of time, but that can be deterministic and therefore easy for a burglar to know that, oh, it's turning on at 7 in the evening and then turning off at 10, right? So you want to randomize that, okay? But you want to randomize it in a way that is realistic, right? That mimics typical human behavior, okay? Somebody gets up in the middle of the night to go to the fridge to get something, right? So that can happen, but it doesn't happen all the time. And so, so you want to be able to mimic that. That it turned out we actually used improvisation for exactly this application. Okay, and then finally, if you think about robotics surveillance as an application, so here the idea is, imagine there is a drone that has to patrol an area, and you have to come up with a trajectory for the drone. Now, if you come up with the same trajectory every single day, when you fly the drone, then the adversary on the ground knows exactly, at 9 p.m. it's going to be here, at 10 p.m. it's going to be there, and so they can plan their, the bad stuff accordingly, right? And so what you want to do is really randomize the trajectory. Of course, you can't do a completely random thing because, we all know energy constraints and there's like other constraints, and you also want to maintain safety. So this is another example where randomness is useful, but complete randomness is not going to cut it. Okay, I'll explain the animation at the bottom pretty soon. All right, so what's going on here? There are 3 different applications. Randomness plays an essential role, but we also know that it's, from my description, completely random behavior also is not good. In the first case, you want to make sure that you satisfy constraints like the turning on and off of lights is realistic and it uses less power. The second, the images you generate have to satisfy certain geometric constraints, realism constraints. And then the third, you have some safety specifications and other things like that. Okay, so the core problem here is you want to synthesize random behavior, but you also want that to be controlled in some way. And that's the core mathematical problem there is what we call as algorithmic improvisation, or what we previously called it as control improvisation. So it's really a framework for automatically synthesizing systems with random behavior that also satisfy formal guarantees. And the systems could be reactive or not. This term reactive is used in formal methods to talk about systems that have to operate in adversarial environments and they have to interact with those environments. Okay. So what you want here are 2 kinds of things, 2 kinds of guarantees. First we call it guaranteed safety. So you may have what I'll explain as hard and soft constraints on the behavior. And then you also want guaranteed randomness. Now the first, guaranteed safety, that's a very common requirement in formal methods. But guaranteed randomness is a slightly different beast. So here what you want to say is that you want a system that exhibits random behavior in a prescribed fashion. I want to see some kind of an distribution, specified distribution over the behaviors. Okay, and that's one of the key novelties here, that randomness, the requirement for random behavior is in fact part of the specification itself. Okay, all right, so now for the rest of the talk, maybe the next 40 minutes or so, I'll explain what control improvisation is at the beginning. I'll give you the mathematical definition. I'll go through some of the motivating applications again. Then I'll dive into the theory of control improvisation, which is really about when can you devise efficient algorithms and what's the complexity and so on. Then I'll pop back to the applications and I'll focus in particular on one of them, the most recent one that appeared at PLDI, which is on design and analysis of perception systems. And then I'll conclude and talk about future work. Okay, so let's talk about control improvisation. So I'll go back to this robotics surveillance application. So here at a high level, the specification is you want to patrol an area in a way that is hard for the adversary to predict. Okay, so what you're seeing in that picture up there is, and I don't know how to get rid of that banner at the top, unfortunately, but let's see if okay, it's just blocking the way, but so you just have to use your imagination. So there's a black line and then a blue dashed line. Okay, so the black line, there's a triangle at the bottom, and that's the starting location. The triangle at the bottom is the starting location of the patrolling robot. So the black line is the patrolling robot. If you can get rid of the top bar, that'd be great. Now the 4 red circles in the middle are locations that the patrolling robot has to visit. Okay, and then there's this blue dashed line. There's a triangle at the top right, and that's an adversary robot or adversary agent. And the adversary agent is trying to basically collide with the black one. Okay, so so what you want here, the specification is, first of all, you want the robot, the black line, to visit each location infinitely often, or not infinitely often, sufficiently often. You also want it to take a route that's closest to the shortest possible one, okay, to those red circles. But you also want some diversity in the route. So every time you run it, you want hopefully a different route. Okay, so the first kind of constraint we'll call as a hard constraint, because here it's the job, the patrolling specification, right? So you want the robot to be able to visit all those locations. So it's a property that it must satisfy. The second one, we'll call it as a soft constraint, because there's a metric, like the distance, and you want, there's a notion of being close to the shortest. So you don't necessarily want the shortest, but you want to get within some epsilon factor of that. And then the third is a randomness constraint, which is not obvious there, but you may imagine that you want some kind of a distribution over the possible routes. Okay, now this surveillance thing may look like this like potentially a toy application, but this is something that we were able to implement on a robotic platform, and then this is showing a deployment in the lab. So this is top view. Those blue things are obstacles. The white squares, the papers, are locations. The location on the extreme left is a charging location where it has to visit every now and often, and then the others are the waypoints that it has to visit. I'll probably get to the specification later in the talk, but the main point I want to make here is that this control improvisation thing is something that you can actually, we got a pipeline down to actual robotic platforms. Okay, so that's application number one, and I will talk a little bit more about that maybe in 10 minutes. The second application is this data generation application. And the idea there is you're training a neural network that has to, for example, for autonomous vehicle, that has to detect objects around it. And you want to generate a diverse set of images. Okay, now this is actually, the way people actually do this sort of thing in autonomous car companies is, as you might know, they actually go and drive around, collect lots of images, real images, right? But the challenge with that is you get the common case, but you may be missing the edge cases. And also the edge cases can occur in different ways, right? So if you actually come across a construction site one day and may have one construction site set of images out of, one day out of 1,000 days, but that may just have certain specific characteristics, and your neural network may overfit to certain properties of that particular thing. And so you want a diverse set of images for every possible scenario that your autonomous vehicle can be in. Okay, so there's a lot of interest in doing this synthetically, using rendering engines for games and for simulators. So that's the context here. And even if you do that, you want the generation to satisfy some constraints, like the objects in the image shouldn't intersect. So you want the realistic stuff. You want a notion of similarity. So you want the synthetic data to be close to real world data. And then you also want diversity. Okay, and so the way we can also think about this is, the first is a hard constraint. Every image should satisfy that constraint. The second is like a similarity notion, that's like a soft constraint. And the third is, again, a randomness constraint. Okay. Okay, so two applications, and there's actually a number of other applications that we have found over the last 4 or 5 years. We actually started this work, the roots of this work are actually in a collaboration I had with a professor of music at Berkeley, and that's something that I talked about in my talk 4 years ago, right? So this whole idea of improvisation actually grew out of a conversation I have with David Wessel on the use of algorithms to make a program improvise the way a human musician would, okay? And we actually had work on a music improvisation approach for jazz, but for other music that could have certain symbolic encodings. Then we also looked at fuzz testing. So software fuzz testing also has very similar characteristics that I can tell you about if you're interested. But the main, now I'm going to try to move to a more abstract level. So if you think about all the applications I've seen so far, they are about data generation. And you can think of data, right, in the same way as you might have learned in a theoretical computer science class, like a Turing machine operating on a sequence of symbols. So think about your data as encoded as a sequence of bytes or some symbols from a finite alphabet. So your data generator is generating these kinds of sequences subject to three kinds of constraints. The first is a hard constraint. That is, every sequence that comes out of the data generator has to satisfy some property. Second is a soft constraint. And in this case, I'm going to take a particular instantiation of soft constraint, which is probabilistic. So you're saying that this generator is random, and most sequences that come out of it satisfy some property. And the third is a randomness constraint, which is a constraint on the output distribution of the generator. Okay, so we say that a problem, a data generation problem that has to satisfy, whose output has to satisfy three kinds of constraint, is an instance of control improvisation. Okay, and what we realized at the time is when we looked in the literature, in the theoretical computer science literature, there really wasn't anything like this problem. So there were other problems that people had explored, both in the theory and in the more systems literature, on problems that have some characteristics of it, but nothing quite like it. So what you're seeing here is just a selection of related work. The columns, hard, soft, random, and reactive, these are the properties of the problem, right? So do you have to generate data subject to hard constraints? That's the first column. Second one is subject to soft constraints, etc. The last column is it also in the context of a reactive setting where the system is interacting with the environment? And so if you think about things like fuzz testing, so mutational fuzzers and generative fuzzers, there are typically some constraints on the type of test cases that you want, or file formats or things like that. And you may have some randomness constraints on, okay, I want to generate something that is uniformly at random from the space of possible inputs. But it doesn't have all three of those. It doesn't have hard, soft, and reactive. And there's no notion of hard, soft, and random. It doesn't have a notion of reactivity. Okay. Then there's also in formal methods, there's this area called reactive synthesis, which is synthesizing planners from specifications. So there are constraints with other specifications, but it doesn't have any notion of randomness. Okay. So that's just a selection of things. So so that's what made us feel like there's actually a lot more to be investigated here, in terms of the types of theoretical problem here. Okay, so now I'm going to walk you through this little example, but also illustrate what control improvisation is in a formal sense. So as I mentioned before, the problem is to generate sequences of a certain prescribed length, let's call that n, from a finite alphabet sigma. Okay, so for this little problem here, let's discretize what the robots do into, so the robot has to take steps that to move around, and each step is going to be moving north, south, east, or west. Okay, so the alphabet of actions for the robot is NSEW, and let's say it can take at most 30 steps, so N is 30. Okay, the hard constraints are going to be that it has to visit all the circles, and it has to avoid collisions. Okay, so there's so there's the robot up in the top corner, or the agent up in the top corner, which is the adversary. And then the soft constraint is going to be that you don't want the path to be redundant, in the sense of you don't want the circle to be, location to be visited twice. If you visited a circle already, you don't have to go back there. But we leave it soft because sometimes to evade the adversary, you may need to go back to where you were before. Okay. All right, good. So hard and soft constraints. I'll talk about the randomness constraint later. Okay, so now let's think about the space of all possible trajectories, right? So that's going to be sigma to the n, all possible sequences of actions of length n. Okay, some of them are going to be bad sequences. Yeah.
So in the definition of how to avoid an adversary, right?
Yeah.
It seems like there's could be two ways, right? One is to use randomness. The other is to also consider where the adversary is as one of your inputs. Mm-hmm. Do you do both, or do you do only one?
Yeah. So if if you want to avoid the adversary, and that's the only thing, and there's no other requirement, then what you're saying is absolutely right. You react to where the adversary is. The missing part of the specification here is the randomness requirement. So you also wanted to make it hard for the adversary to guess where you'll be, not because the adversary will collide, but because the job of patrolling is to actually make the path of this hard to guess. Right? It's sort of like, think of a museum robot, right? So the museum robot takes a route trying to go drive around a museum, and you want to make sure that the burglars don't know where the robot is going to be, right? So that's the other part of the specification here. Okay, so right, so sigma to the n is a set of all possible paths, and some of them are bad, right? The ones that collide in this case. And so what you want is everything that excludes the bad behavior, right? So you want things that satisfy the hard constraint. So that's the red set here. We'll call that capital I. Okay. Now this red set could contain things that violate the soft constraint, like visiting the same circle twice. And so ideally what we'd like to be is inside the light blue circle, right? Which is the set of all things that satisfy also the soft constraints, hard and soft constraints. Okay? Okay, but there's also this randomness constraint, which I haven't talked about yet. So that's going to be the next part of the definition. So here's the formal definition of a control improvisation problem. You're given a hard constraint H, a soft constraint S, a length N, and then you're given, for the soft constraint, there's a probability with which you can violate it, which is epsilon. And then you're given some parameters, lambda and rho. And first of all, we're going to define what's an improvising distribution. Okay, so this is something that maps sequences to probability, so assigns probability masses to sequences. And the first constraint, the hard constraint, says that everything in the support of the output distribution has to satisfy the soft constraint. So it has to be in I, the red set. Okay. The soft constraint says that with probability 1 minus epsilon, you have to be in the light blue set. Okay. And the randomness requirement, which I haven't talked about yet, but here it is, okay, is that for every sequence that's in capital I, the red set, the mass you assign to that has to be between lambda and rho. So rho is an upper bound, lambda is a lower bound. Okay? So the way to think about the randomness requirement here is that the rho is saying something like, don't generate any sequence too often, right? It's an upper bound on how often you generate it. The lambda is saying generate it at least so much, right? And what we found is lambda and rho can be useful in different applications in different ways. So for example, in fuzz testing, you want a lower bound typically, because you want to be able to hit every sequence. The upper bound is not that important. In the case of music, or even this patrolling example, the upper bound becomes more important because you want a diversity of outputs. So that's the kind of thing. So we really can play with these parameters depending on the application. Also, the interesting thing is using lambda and rho, you can specify distribution requirements as well. So you can specify uniform random distribution using lambda and rho, as for example. Okay, so yeah, question? I'll give the reactive definition next. Okay. All right, so this is the non-reactive setting. So the environment is not reacting to what the system does. So a problem instance is going to be this 6 tuple, right? Which is hard constraint, soft constraint, length, epsilon, lambda, rho. And we'll say that the instance is feasible if an improvising distribution exists. So not all instances are feasible, right? And then the improviser itself is a probabilistic algorithm that samples from this output distribution. Okay, so again, this little toy example. So let's, again, for the sake of argument, imagine that the cardinality of capital A is just 3. There are just 3 paths possible, okay, A1, A2, A3. And then let's say that in I minus A, which is things that satisfy the hard constraint but not the soft constraint, there are 2 sequences, I1 and I2. And so one strategy I can use, if I say that I cannot generate any sequence with probability more than a quarter, so rho is a quarter, so I can't generate any sequence probability more than a quarter, I can't simply sample from the light blue set because I'm going to go above a quarter, okay, because there's only 3 of them. So what I need to do is sample from light blue some of the time and then sample from the red that is outside the light blue some of the time. Okay, and one possible strategy is to sample I1 and I2 with probability 1/8, and then A1, A2, A3 probably 1/4. Okay, this is again highly simplified example where you can actually see the elements of the set. Typically, the sets are really huge. Okay. Now let me get to the question that was asked, which is how do things change in the reactive setting, right? So in this case, the adversary is actively trying, is not just driving some fixed route, but is actively trying to chase and collide with the robot. So the setting here is very similar to the traditional reactive synthesis setting, where you can model it as a two-player game between the system and the adversary. And we'll think about it as a turn-based game. So first the robot moves, and then the adversary moves, and so on. Okay. The main way in which we lift the definition to the reactive setting is we say that we need to satisfy the hard, soft, and randomness constraints for every possible adversary. Okay, no matter what the adversary does. Okay, and then we go. The improviser is not just generating a sequence, but has a strategy, which is basically, you can think of it as a branching structure, where the improviser makes a step, and then if the adversary does this, then it'll do something. If the adversary does something else, it'll do something else, etc. Okay. And this whole thing is bounded time. So we're only looking at strategies that will run for length n. Okay, so that's one key point of difference with the traditional literature on reactive synthesis. Okay, so for this little toy example, the hard constraint is the same. You want to visit the 4 circles and avoid the adversary. The soft constraint is also the same, except I now have a probability. I want to say that 3/4 of the time I will visit each circle exactly once. The randomness requirement is that I only have a row, an upper bound, and I actually want the smallest possible upper bound, right? So in this case, it turns out to be around 10 to the minus 12. And using this, we can actually, we have a generator that takes in these kinds of constraints and can produce plans, like the ones that you see animated here. Okay. Good, so now so far I've talked about the definitions. So control improvisation and then reactive control improvisation. Now I want to talk about algorithms and complexity. So the first question is, if I have a problem instance, when is it even possible to solve it? Like, does a solution exist? And how do I find that? Okay. Now, to our pleasant surprise, it turned out that this question is quite easy to answer. Easy in the sense of mathematics, not that easy computationally though. So it just requires these sets I and A to be large enough. Okay, so remember, I is the set of all possible improvisations, everything that satisfies hard constraints. A is the set that satisfies additionally the soft constraint. Okay, and the theorem we have is, if you're given a problem instance, then it's feasible, that is, the solution exists if and only if the set I, set of all possible improvisations, is at least 1/ρ. Rho is the probability, that is the upper bound probability on generating any output. And then the set A, which also satisfies the soft constraint, should be at least 1 minus epsilon over rho. What's actually interesting about these inequalities is that they kind of match what you might think intuitively, right? Because, for instance, if for the first one, if I was not as big as 1/ρ, then you're not going to be able to sample from within I with probability at most rho, right? There's not enough things in it. And it's sort of similar reasoning for A. But the nice thing is this theorem works if and only if. And if you're interested in the reasoning, I can go over it later. Okay. All right. So now, okay, what do you need to do then? You have to be able to count the cardinality of I and count the cardinality of A, and then just compare with these inequalities, right? Now, if I and A are small, that's not a problem. If I and A are huge and they're presented to you symbolically, that can be challenging, right? It's like typically a Sharpie complete problem. So that's a computational challenge, but at least in the terms of the mathematics, it's very simple. Okay, so now what is an improviser, right? So an improviser is, or what is the problem we're solving? So first, we have this notion of what we call an improvisation scheme. Okay, the idea here is you have a problem instance, and the improvisation scheme is something that takes a problem instance and produces an improviser, produces an algorithm, such that every time you run that algorithm, it does something different. Right? That's what the output is. That's an improviser. So think about this as really a synthesis algorithm, right? In the sense of program synthesis, right? The orange box is generating a program, but the program is a probabilistic program. Okay. And now what we want is an efficient improvisation scheme, right? Ideally polynomial time. So what that means is that if I have a certain class of problem instances, then what I would like is a scheme S such that given any problem instance, if that instance is feasible, it will return an improviser, otherwise bottom. So this is just saying that you want it to be correct, right? And then the second is saying that the scheme as well as the output algorithms it generates have to run in time that's polynomial in the size of the instance. Okay? So that's what we want, ideally, right? A polynomial time improvisation scheme that also generates polynomial time improvisers. Okay. Now, in the initial work on this, we didn't really have a clear idea of how to do this as the specification type changes, right? So hard and soft constraints, I've kept them pretty abstract so far. They're just sets of behaviors, right? But in actual, in program verification, we know there are many ways in which you can write specifications, and some of them are more powerful than others. And so what we've found is that the complexity of the problem varies with the type of specification you write. But what's really nice, and this is all due to Daniel, is that we found a common meta algorithm that works for all specification types. So it's like a generic improvisation scheme that works if you can do 4 things really on the types of specifications. So first, you want to be able to think of specifications as sets. So you should be able to intersect the sets and take the set difference. This is typically quite easy. It works for all specifications that are sets. Then the second thing is you want to look at specifications that are over bounded length sequences, right? So some specifications are they're over infinite length sequences, and those are not things that we are looking at. Now the third and fourth are the tricky ones. So you have to be able to count the number of words that satisfy a spec. And the fourth is you need to be able to sample uniformly at random from the set corresponding to the specification. Okay, and these can be non-trivial, as I mentioned, right? So for instance, if your spec is just a Boolean constraint, then this is essentially the problem of model counting the number of satisfying solutions or sampling from the set of satisfying solutions. But if you can do those 4 operations, then and you can do them efficiently, then there's a polynomial time improvisation scheme. Okay, and this is how it works. You construct the specifications that correspond to the hard constraints with I, the soft constraints A, and then the set difference of the 2. You count I and A, and you check those feasibility inequalities, right? And if it's feasible, then there's an algorithm that a very simple algorithm where you can just sample from either A or I minus A with the right probabilities. Okay, and of course 3 is a highly abstracted version of the actual algorithm, which is in the paper. But that's how it works. And so it just uses those 4 operations as oracles. Okay, so what can we do efficiently? So it turns out if your specifications are DFAs, so they're regular languages that can be expressed as DFAs, then you have a polynomial time scheme. If it's an unambiguous CFG, which can be the case for fuzz testing applications, then also it's polynomial time. Yeah.
The question is, how would the reactive system be modeled as a DFA?
So remember, this is so far this is not the reactive setting. This is the non-reactive setting. Okay, I'll get to the reactive setting, but you can think about in the reactive setting, you're looking at things like safety games or reachability games, right? So there, the controller, the system, is a finite state transducer. The environment is similar, right? So that's the correspondence. Here, of course, we are in the.
So there, you have to come up with a random strategy.
Exactly. You have to come up with a random strategy, right? And remember, here we're talking about DFAs as opposed to Bookie automata because they're all finite length sequences. Okay. So but anything more than DFAs and unambiguous CFGs gives us higher complexity. So we have polynomial time for those 2 cases, and then if you have a regular language but you're expressing it as an NFA, then our algorithms, I mean, we can't find anything that is better than Sharp-P in the size of the specification. Okay, and it turns out, I mean, I haven't completed this picture, but if you have specifications that are more complicated, it can even become undecidable. Okay, Also, if you, you could think of the specification as given as explicit form. If you give it in symbolic form, then we can have approximate polynomial time improvisation schemes that assume that you're using a SAT solver as an oracle. So you just count the number of calls to a SAT solver, not the actual complexity of solving SAT. Okay. All right. So now to the reactive case, right? So it turns out, if again the feasibility for the reactive setting is very similar. It also reduces to counting, but you're counting something different. You're counting not the cardinality of the things in the specification, but the number of ways the system can win the two-player game. But the inequalities look almost exactly the same, except what's on the left-hand side is different. Okay. And so what that thing is something we define called the width of the game, which is the number of winning plays. So a play is basically a sequence of actions alternating between the system and the environment, between the two players, right? And so if the width of the game is big enough, then the problem is feasible. Okay, that's what it means. So for this, in the interest of time, I'll skip over the definition, but the gist of it is that it turns out that this feasibility check is very similar to what we had in the non-reactive case. Okay. Now, what can we do in terms of efficient algorithms? Again, for DFA specifications, we have an efficient scheme, and what we mean by DFA specification is really the play, if you think about it as a sequence of symbols, right, alternating between the two players, that should lie in a regular language represented by a DFA. And so, and there are other ways of representing regular languages that also give us polynomial time implementations, but anything more than that, including NFAs, CFGs, and then also versions of linear temporal logic and linear dynamic logic for finite length traces, all of those are higher complexity, turns out to be p-space. But a comment there, so this is exactly the same complexity as standard reactive synthesis. So coming up with a randomized strategy seems to be no harder than coming up with a deterministic strategy, which is nice. Okay. So anyway, that was a bit of a whirlwind tour of the theory, right? But I hope I gave you a sense of what is there. Now I'm going to get into a lot more practical stuff. So we'll talk about this application of designing analyzing perception systems. And so here the motivating example here is you have an autonomous vehicle, you have a camera in front of that vehicle. It's fed to the output of the camera is fed to a deep neural network that has to essentially detect what's in the scene. Okay, so what is really this notion of a scene, right? This word is used quite informally. So for us, a scene is a configuration of objects in 3D space, right, along with the attributes of those objects, and possibly if those objects are dynamic, then attributes of the dynamic objects, like the velocity of the car, the heading at which it is heading at the current instant, and then that over a period of time. Okay. As I mentioned, what people do a lot is drive around and collect data. That's pretty expensive. It's also not going to produce a comprehensive data set, especially of edge cases. And so we're looking at this case of what simulations to run to generate a diverse data set. The challenge with that is that this is a very large, high-dimensional space. So if you just think about, I want to generate images of a car, right? Then there's a lot left unspecified. Like, what's the model of the car? Where is the car in the frame? How is it? What's the orientation? Are there other cars around it, right? What's the time of day? What's the weather? So there's lots of, and then there's lots of other implicit geometric constraints that come with each domain. Right? So I'm talking about cars here, but a lot of the stuff I'm talking about in this section of the talk also applies to other kinds of scenes. Okay, and then you might want to kind of specialize it and focus on a particular type of scene. Like I want to look at highway traffic, not city traffic. So it turns out that this data generation problem is also another instance of control improvisation, as I've mentioned before. So you have these hard constraints, which are saying that things don't intersect, for instance. And you have soft constraints, which are like similarity. And then you have some randomness thing, right? I want to be able to generate images uniformly at random that satisfy these constraints. Okay. And so, or you might, the soft constraint could be something like, I want to generate bumper-to-bumper traffic scenes, of which most of them, 80% of them, should be daytime, right? And you might say, oh, the gap between the cars should follow a certain distribution. Okay. So how do we encode these? And so we thought about this, and we could have gone with the hard, soft, and randomness constraint that we used in the previous case for the robotic planning example. But instead, what we found is that it's a lot easier to create a domain-specific language to help people just write these specifications. Okay, and in fact, because the specifications, some of them are probabilistic, a probabilistic programming language seemed to be the right fit.
So is this also true to represent a reactive control? Can that also be written as a probabilistic programming language? I guess this is non-reactive. Right? This is not.
In this case, it's not reactive, right? So in the case of reactivity, so it's talking about specifying, writing the specifications. So
the solution
you could still write the specification in this way. Then you would have to specify constraints on what the environment can do. I suppose you could also write them here. What you'd have to do is extend the specification language to be able to talk about sequences of actions. And right now, we don't have that capability yet to, for example, write a temporal logic property or something like that in the language. You can do this in the language currently by explicitly writing down constraints over parameters that encode a sequence, right? But yeah, I mean, I think, so the short answer is yes, you can do it with the current language, but it's not elegant. Okay, so what the language is, so the language that we've created is called Scenic. And what it does is it helps you define a distribution over possible scenes. Okay, remember, a scene is a configuration of objects in 3D space along with the attributes of those objects. So for instance, if you have your scene is bumper-to-bumper traffic, it turns out it's about 20 lines of Scenic code. And Scenic is a DSL. So we have designed it in a way that we can write concise, short programs that are also readable, that can capture common geometric relationships. Okay, and furthermore, one of the reasons to design a DSL is because the back-end sampling techniques, the sampling algorithms can be made much more efficient because of the ability to exploit domain structure. Okay. And then we can write your hard and soft constraints similar to other control improvisation settings. Okay, so one of the ways we envision the use of Scenic is to design and analyze perception systems. So like neural networks that are used to detect objects. So the way this works is you start with a Scenic program. I'll show you an example of it, but you already see what the syntax looks like, which is down there. It's like a cross between English and Python. And so it goes through the interpreter, which is the Scenic sampler. And each time the interpreter runs, it produces a scene. Now, scene is an actual configuration. So a Scenic program defines a distribution over scenes. The sampler or the interpreter produces, each time it runs, it produces one scene. And that's like a layout that you see here. So it's like a schematic layout of where the car is, where something else is, etc. You take that and you feed this to a simulator or a renderer, and that produces data. Okay. So a lot of simulators or game engines have some kind of format, input format, and basically we translate the output of Scenic into that format. Yes, question?
Where is the improvisation scheme here?
So the improvisations, yeah, good question. So the improvisation scheme here is really in the generation of the sampling strategy, right? And I'll have one slide about it, but there's more there. Yeah.
So is one scene like one clip or one series of clips like a video? Because cars would change positions and.
Exactly. Yeah. So for this app, what I'll talk about, different applications have different notions of what a data item is. So in the case of, I have a neural network that has to detect an object in an image, a data item is one image, right? In the case of the use of Scenic, which I'll show at the end of the talk, where you want to find counterexamples for an autonomous vehicle controller, where it shows that here's a sequence of actions that takes it into a bad state. There it is a sequence. Okay, so the Scenic can do both. All right, so here the application I'll talk about for the next 5 minutes is just images. And so you can generate test data, you can generate training data as well, and you can use that to augment real data. Okay, so one of the applications that we use Scenic for is to debug things like neural networks for object detection. So here, this is a concrete example of an image we generated and this is all generated using the Grand Theft Auto 5 game engine. So that's a car with a racing stripe on it, and one of the best academic object detection neural networks that is out of Berkeley thought that there were 3 bounding boxes where there's just one, right? And also with reasonably high probabilities or confidence levels. And so we went back to the people who created this and we said, okay, here's an example of a buggy input. And they thought maybe it's the racing stripe because a data set typically doesn't have cars like that. And what we were able to do is use the Scenic program that generates this and then do delta debugging on that program. So change the model of the car, the position of the car, et cetera, and do this efficiently. And what we found is actually it wasn't the stripe at all, and it was something really weird, like the distance between the camera and that car. Okay. Anyway, so you can do that sort of thing with Scenic. It's a probabilistic programming language, and there's been a lot of work on probabilistic programming language, including here at Microsoft Research by Sriram and other colleagues. And so I just want to situate Scenic in that work. But before that, let me take the question.
Yeah. So one thing I was quite curious about the previous example that you mentioned is that typically, right, was the picture discovered first and then the Scenic program written, or was the Scenic program written first and then the counterexample discovered?
Yeah, good question. So there's 2 use cases for Scenic, right? So one is you can write a Scenic program and you can use it to generate data, and then you can find misclassifications, right? So that's one. Once you found a misclassification, then you can think about doing delta changes to the Scenic program. The point is, once you have a program that is generating data, it's much easier to explore the neighborhood as opposed to the typical adversarial example thing where you're like perturbing pixels or whatever, right? So that's sort of, we want to be able to find out what is going on. Why did the neural network come up with a bad output in this case? And having the Scenic program in the first place makes it a lot more useful. Yeah.
So should I think of the Scenic sampler as some like MCMC like sampler?
The Scenic sampler, actually, you can use any of the techniques that have been produced and published in the PPL community, right? And in fact, our existing sampler, the first sampler, which we already did pretty well, is just doing rejection sampling. But you could use MCMC, you could use, in some certain cases, you could actually even use the work that's been done in random sampling from SAT problems.
Yes, because it seems that this is quite interesting from a computer graphics point of view. I think this can be used to generalize several SIGGRAPH papers which came out. So what they were trying to do is do fancy stuff. For example, one was about furniture layout.
Right.
You want to lay out the furniture.
Correct.
There was one about you have some pebbles and you want to create a geometry in which small pebbles are below and big pebbles are above. So the system is really unstable, but physically it should not fall down.
Right.
Or you can put pebbles into an arch.
Yeah.
And they were all using MCMC to generate these systems in which you have some hard constraints with physics, some soft constraints, and you want a variety.
I see.
Like furniture layout, furniture should not intersect.
Sure. Right.
And it seems that you can take these and write them as Scenic programs. So
yeah.
This will be pretty interesting from a graphics point.
Okay, great. We've had that in mind also because we are not the first people to propose PPLs for this sort of scene generation problem, but we feel that our syntax is a lot more concise than what other people have proposed.
Yeah. That's what I'm saying. That I think graphics people might be very interested in this.
Right. So
There is, by the way, a probabilistic programming language that has been designed for the graphics
Picture.
vision.
probably.
Yeah, picture. That's the one
Right.
with MIT and Pushmeet, I think. Probably.
Yeah, I think so.
Vikas Mansinga and Pushmeet, I think as well.
That's, yeah, and there's also, so I think, okay, there's another person whose thesis came out of MIT. I forget his name now, but anyway, Richie, it's right there, right? Daniel Richie, number 2. So, and the Kulkarni et al. is the one that you mentioned, right? So there are a few that have already appeared here on this.
Yeah.
But the main difference is here, right, is, so first of all, our emphasis is on generation, not inference. A lot of the PPLs for graphics, actually even those were on scene understanding, right, and vision, scene understanding. And so that was more on the inference side as opposed to generation. The second is the domain specificity. So they use PPLs that are quite general, and Scenic is not even Turing complete. So there's a big gap, and we restrict Scenic in certain ways that makes sampling much more efficient. Okay. Okay, there's also work that is not programming language based, right, on generating data. And the main difference with Scenic is that having a program gives you a lot more control, and it's also more interpretable. Okay, so let me walk you I'm probably over time, but I hope I can go another 15 minutes and tell you a bit more about Scenic. So consider the example of a badly parked car, and I'll just walk you through the creation of a Scenic program to model this. So what you're seeing on the left there is, so you have this this is a schematic, so the triangles correspond to the objects, and the pointy end of the triangle is showing which way the object is facing, right? So on the left, you see this triangle that's facing this way. That's what we call the ego object, right? That's the object from whose viewpoint you're going to construct the scene. And that's going to be a car at this intersection. And so the first line is basically saying from the Grand Theft Auto library that we have interfaced to Scenic, we're going to import the notion of a car, a curb, and a road direction. So the point is Scenic is not really about autonomous cars per se, right? So if you interface it to a library, a renderer that can do that, then you can use it for that application. And then next what you say is the ego object is going to be a car itself. So if that car moves, then the viewpoint moves. And then you're going to say, well, look at a curb region that's visible, that's in the view cone from that object, and pick a point with an orientation on that. So let's zoom into that. So what's happening there is you look at what's visible, and then you look at the curb region, which is the part outlined in black, and then you pick a point on that, and the point has an orientation, which is along the road direction. Okay, let's call that spot. Now, when I say pick a point on the curb, implicitly you're picking a point uniformly at random from the curb region. Okay, so even though there's no use of the word uniform or normal or any distributions yet, there are implicit distributions with all these objects. Okay, so the variable spot itself is a random variable, right? Then you pick a bad angle to park the car at, and so that's in this case is defined as between 10 and 20 degrees, either left or right. That's the 1 minus 1. And here we are saying it has to be uniformly at random. And then what you do is you place a car left of that spot, offset by a vector. This is the Smalltalk vector notation, so it's 0.5 meters that way. Okay. And then it faces the bad angle relative to the road direction. Okay. Now, in Scenic, every object has its own local coordinate system. So this is why we need things like specifying that it's relative to something else, right? Okay, so that's the Scenic program for the badly parked car case. The first is just importing these objects, and then the rest of it is the code. Okay, and then once we do that and we connect it to the GTA-based generator, you get a sequence of images like this. And what's happening is that the other attributes of the scene, like the model of the car, time of day, and so on, are just being sampled uniformly at random. Okay? Now, from a language perspective, what is new in Scenic, one of the main things that's new is this notion of specifiers. So, I mean, the notion of specifiers itself is not new, but the way in which we're using it, this application, is new for scene generation. And so we have these things that are highlighted in yellow, right? Which is facing towards, one object facing towards something, or a car at a location, right? These are really, think of them as ways to programmatically express dependencies, geometric dependencies between objects, right? And we have 9 possible specifiers, and they're all written in a way that is close to natural language. Okay, and then one of the key points, actually this is something that Sriram helped us understand when he visited Berkeley, right? So what we did is we designed Scenic to be a language in which we can write down dependencies in a very natural way. Dependency between objects. And so what this translates to is in the back end, when you have random variables that model the different objects, you have the dependencies between those random variables expressed very naturally, captured. And then when you do sampling, you use the dependency structure to do that efficiently, right? Okay. And then you have things like, this relative to road direction. So you can think of that as a function that tells you how to sample or produce the angle in this particular case. All right. So so the domain-specific sampling techniques really correspond to ways in which you can prune the space from which you're going to sample from. Okay. And one of the ways we do this is you can think about the geometric regions from which you want to sample, and we basically dilate or change those regions in order to prune away infeasible parts. So for instance, a concrete example is, here's a map of the roads network in the Berkeley area, and what we wanted is to be able to generate a scene where there's a ego car and then there's a taxi, and the distance to the taxi is less than 5 meters. And the relative heading of the taxi, so the angle in which the taxi is heading versus the angle that the orientation of the taxi, the angle between the orientation of the taxi and the orientation of the ego vehicle should be between 15 degrees and 45 degrees. And that's kind of a funny angle for cars to be oriented if they are on the same road, but it's possible if they're at an intersection and one car is going that way and the other car is going this way. And so what you see here is that we are able to automatically, in this road network, mark these green regions, which are all the places where we can sample from, and then prune away all the red stuff, which are parts of the node network where we don't have to sample from. And you can greatly reduce the space for the backend sampler. This is one example of the kinds of domain-specific sampling techniques that we can do. Okay. So very quick summary of the applications of Scenic. So one application I haven't talked about yet is just to do design space exploration, right? So, and you can use this not just in the autonomous driving application, but in fact, one of the other things we looked at is in robotics. Like if you have this kind of Mars rover that has to navigate to a location which is marked by the flag, it can climb over rocks, but it can't climb over pipes, right? And so now you want to be able to generate test cases that are really challenging for the rover. And so they can be things like this, right? Where there's the 2 pipes blocking the path, and there's only a very narrow gap which has a rock in it, and it has to climb over the rock to get past, right? And you can write a Scenic program, very short Scenic program that generates a lot of these challenging things, and you can explore how the system works. I already talked about this one. We can also apply Scenic to generate better training data, in particular training on cases that are hard for the neural network. For instance, for the same neural network that had this issue, we found that it was not able to detect cases where one car is blocking another partially. It was missing the car in the back. So occlusions is a challenging thing. And we could actually, what we did is we used a Scenic program to generate more data and use that to augment the training set by adding a small amount of synthetically generated images, and we improved the precision significantly on the hard case, and we didn't lose precision on the original case. All right, so now I want to conclude. So that's a very quick overview of the work on Scenic. In conclusion, I think this idea of algorithmic improvisation has really developed into a very interesting set of directions over the last 4 years since I last spoke about it. There's lots of applications that you see here. I think in particular, probably due to my own interests, we've been looking more at the applications to save autonomy, but I think there's applications much beyond that, like what Rahul mentioned in graphics. And more generally, I think this is a new class of randomized formal methods that I think can be quite useful in the design and verification of various kinds of systems. Okay, what's next? I think there's a lot more to explore in the theory of algorithmic improvisation, and maybe just have scratched the surface in terms of algorithms and complexity there. And I think there's use this for data generation for a variety of applications. Modeling dynamic agents, I think, is a very interesting application. This is something that Sriram also talked about. And our current use of Scenic, we've used it in that context, but we think we need to improve the language for that use case. And one of the places where this need to model dynamic agents comes up is in verifying machine learning or AI-based systems, that especially autonomous systems. And we recently put together a toolkit that appeared at the CAV conference that we call the Verified AI or Verify toolkit. And I want to give you a sense of that and then show you a use case of Scenic in that case. So in this toolkit, by the way, it's open source, Python-based. And what you can do with it, if you just focus on the right-hand side, you can do what's called falsification, which is property-guided, so formal specification-guided bug finding. You can do fuzz testing. You can generate counterexamples and then do some analysis on the counterexamples. And then you can do data augmentation, which is you take the output, like counterexample that you generated, and then use that to augment your data set and retrain your ML components. And you can also do synthesis of hyperparameters and model parameters in your ML models. But you can do that in a property-guided way. So you can say, I want to synthesize my hyperparameters so that after training, the resulting model in the system will satisfy a property. Right? It's a kind of a long thing I said, but the idea is you're using a formal specification to guide the synthesis. Now to use it, what you need is, so this toolkit is based on simulation. So what you need is you want to feed your modeling, in this case I'm talking about CPS, you want to model the controller, the model of the objects, the plant, what is called the plant model, and then the perception components like the neural networks. So that's like the system description. You want to model the environment, for example, in a Scenic program, and then you want to specify the property. And then you can use these different use cases. So an example of what we did with this is to analyze the behavior of an autonomous vehicle that is supposed to navigate around a stalled car or like some kind of a construction site. So what's happening here is that the maroon car down there is an autonomous vehicle, and initially it's doing lane keeping. And the way it's doing lane keeping is using standard edge detection on the lanes. Okay, so no machine learning there, but it's a bit classic AI algorithm. And then it also has a camera that feeds to a neural network that is looking out for these sorts of stall sites that are marked by orange cones. And so if it detects one of those, it tries to estimate the distance to that site. And if the distance is below a threshold, it executes a lane change and tries to go around this. So there's two things going on. There's lane keeping, and then there's at some point neural network says, oh, there's something in front, and you have to navigate around it, and then it does a lane change. Okay, that's the situation here. On the left is the Scenic program that we wrote. And in the Scenic program, what we are trying to specify is what the environment looks like. So where is the blockade site? Right? It's near a curb and it's point with an orientation. And then where are the cones and where is the disabled car? And what's the angle of the disabled car? So that's the sort of thing that's being specified there. Okay, we can also specify if you're talking about other environment objects and they have associated velocities and so on, you can specify those as well, but I don't have it in this example. Once you have that Scenic program, then we can essentially we can generate lots and lots of initial conditions for simulation. So you can think about this as the analog of fuzz testing. So you're seeing that visualized here is generating lots of cases where there's a stalled car, there's cones around the car, and then there's the red vehicle is some distance away, okay? And it varies the position, it varies the model, colors, and so on. Okay, what you're seeing at the bottom is the camera view from the autonomous vehicle. All right, now I'm going to show you next the application of falsification, okay? And let me just pause this for a second and explain what you're going to see. So, so what you're seeing is the visualization of the falsification algorithm. So the falsification algorithm is an iterative algorithm. It starts out with a correct behavior, and then it tries to direct the search towards unsafe behaviors. Okay, so it's like basically an iterative loop where the first simulation you'll see is just fine. Okay, and then iteratively we'll show simulations that go towards collisions. Okay, so initially it starts out with lane keeping, it detects the car, it goes around it, everything seems to be fine, right? And now you'll see the color of the stalled car changes, the positions change, the cones, the location of the cones change, etc. And there was the first crash where it just grazed the rightmost cone. And now iteratively it finds more and more egregious crashes, getting closer and closer to the car. Okay? And so that's what the falsification capability is doing. So what Scenic does in this whole setting is it provides you a way to randomly explore those configurations that you want to run the simulator in. And this last one was particularly interesting. So here what we found was, automatically, what we found was a case where the environment car was the same color as the cone. And so what happened here was that the autonomous vehicle's neural network, okay, let's see it here. So if you see down here, right, the stalled car looks orange. What happened was the neural network had basically trained itself based on the color of the cone. And so it saw the orange car, it thought that it was a cone, and it sort of misestimated the distance, and it executed the lane change way before it should have, but it ended up being a bad lane change, and it hit the car anyway. So anyway, so that's the kind of thing that you can do with a language like Scenic, right? You can basically use it to do this kind of systematic simulation-based testing of these kinds of systems. So that's all I had to say. So both Verify and Scenic are open source, and they're available off of that GitHub site and my webpage. And I'm happy to take any further questions and happy to discuss more. Thank you.
Okay, so let's thank them. Thank you.
Okay, thank you.